Hello everybody. So, if you recall, we were discussing second law of thermodynamics, and I have told the two very important statements of second law of thermodynamics. One is Kelvin-Planck statement, and from that statement we could get the concept of a heat engine. Then I have also given the statement which is given by Clausius, that is Clausius statement of second law of thermodynamics. From there also we could get a very important engineering device which operates in a cycle. It can be called either a heat pump or a refrigerator. So, if we start with, so Clausius statement gives us a configuration like this. This is where we are taking some thermal energy Q2 from a low temperature body, and with the help of mechanical work supplied from outside, we are transferring or transporting this thermal energy to a high temperature body or high temperature reservoir, which is at a temperature T1. If we are interested in transferring heat to a high temperature body, we call this device a heat pump. If we are interested in extracting heat from a low temperature body, we call this device, the same device, as a refrigerator. And I will draw your attention, you will find that this device, as far as the direction of energy transfer is concerned, is just the opposite, just the reverse of the device we called heat engine. So, it is some sort of a reversed heat engine. Now, for heat engine we have defined efficiency. So, in this case also we can define some sort of a figure of merit. We do not call it efficiency, we call it coefficient of performance. So, you see, let me draw it quickly. So, this is T1 and this is another reservoir at T2. In between there is a cyclic device which is being operated with the help of work supplied from outside, and by this supply we are able to take Q2 amount of heat from the reservoir at T2 and supply Q1 amount of heat to the reservoir at T1. So, we are defining coefficient of performance, we call it COP. It is defined as desired effect produced by energy supplied. This energy supplied, it has to be understood that the energy which we supply by paying something, the energy for which we are paying, that is meant by the energy supplied over here, and in this device we pay for the external work which we supply to run this device. So, W is the energy supplied. Now, if we are thinking of a refrigerator, COP refrigerator, then our focus is the amount of heat we are extracting from the low temperature body. So, this will be Q2, that is the desired effect, and W, this is what is the energy which we pay for and which we are supplying to run this device. So, it is Q2 by W, and from first law what we can write, this is Q2 and this is Q1 minus Q2. So, this will be the COP of a refrigerator. In similar fashion, we can get COP of heat pump. So, that will be Q1 by W, that is equal to Q1 by Q1 minus Q2. So, COP of heat pump will be Q1 minus Q1 divided by Q1 minus Q2. Here again I like to draw your attention to one fact, that as the efficiency of a heat engine will always be less than 1, the COP of heat pump will always be more than 1. Why? Because it is Q1 divided by Q1 minus Q2. Q2 is some sort of a finite quantity, non-negative finite quantity. So, that is why this part will be less than Q1 and COP of a heat pump will be more than 1. So, by this we have got we have understood hopefully the two statements of second law of thermodynamics. There could be many statements, but these two are the most important statement. These two are the most relevant statement for engineering application, and obviously you will find these statements are also very important for waste heat recovery. And then how to define the figure of merit for these two devices, which comes from these two statement. One is heat engine and another is heat pump. So, that also has been learned. Now, once we have done this, we have come to the engineering domain, that we have got devices where energy conversion is possible continuously. All the devices which we are talking about, they operate in cycle. That means, they produce or they have the energy conversion continuously. Obviously, as an engineer, one will be interested to know or to have these devices operating at the best possible condition. For example, we will like to have the highest efficiency of a heat engine. When we are converting thermal energy into work, we would like to have the maximum amount of thermal energy to be converted into work. And when we are having heat pump or refrigerator, we would like to have the highest COP of the refrigerator or the heat pump. Now, is it possible to have some sort of principle then which guides us to know what is the highest possible performance of these devices? And is it possible to have, when the conditions, the input conditions are given, is it possible to evaluate what is the highest possible conversion? So, these are the questions which we like to which we seek for which we seek answer, and fortunately answer is already available in second law. Probably we have to learn little bit more. Now, here comes the epoch making findings of Carnot. So, now we go from heat engine and heat pump, we move to Carnot principle. So, Carnot, he was bothered regarding the low performance of heat engine. In those days, of course, steam engines were there, low performance of steam engine, and he tried to find out some means why the engines are not performing as they should perform. What could be the best performance out of a heat engine? So, that is what he was pondering about, he was searching. And then he came with some sort of simple, but very far reaching conclusion out of his research, and that is that these devices are operating in cycles and best performance can be obtained from a reversible cycle. So, what is a cycle and what is a reversible cycle? So, let me write this is very important. reversible cycles give best energy conversion. This is very important. So, though Carnot did it for in the context of heat engine, but it is in general one can say that reversible cycle gives the best performance for energy conversion. Now, what does it what is meant by this? So, a cycle, suppose this is a thermodynamic plane, there are two coordinates of thermodynamic properties, and in this thermodynamic plane we have got a cycle. So, cycle could be represented like this. So, there are number of processes, so 1, 2, 3, 4 like this. There are 4 processes, and let us say the processes are like this: 1 to 2 there is one process, 2 to 3 another process, 3 to 4 another process, and 4 to 1. So, if we have started from point 1, we are coming back to point 1. So, this is a cyclic process or a cycle. A reversible cycle means that all the processes are reversible, and if all the processes are reversible, then the direction of the cycle can be reversed. And if we reverse the direction of the cycle, then there will not be any change elsewhere, neither in the system nor in the surroundings. So, here the concept of reversibility is coming. At the beginning, probably in the last lecture, I have told that second law gives us the concept of irreversibility. Basically, it gives us the concept of reversibility and irreversibility. So, this is your concept of reversibility. So, if all the processes are made reversible, then the cycle is a reversible cycle, and Carnot postulated that a reversible cycle will have the best performance as far as energy conversion is concerned. Now, if we are having a reversible cycle, then what is happening? If we are having reversible cycles, then Carnot has given two statements. These are again postulates of Carnot. First postulate is that between two given temperature, only a reversible heat engine cycle will have the highest efficiency. So, let us say the temperature limits are given. Let us say this is T1, this is the source temperature, and let us say this is the temperature T2, that is the sink temperature, and T1 is greater than T2. So, in between this we can have heat engine cycles. So, let us say this is one heat engine cycle, and we are having some sort of work out of it. So, this is reversible, and then we are having one irreversible cycle. So, this is also taking heat and converting it into work, rejecting the rest of it into the reservoir. So, in no case, whatever may be the design, whatever may be the working principle, in no case the irreversible engine will have higher efficiency than a reversible engine. Okay. If we have number of irreversible engines, all the reversible engines will have lesser efficiency compared to a reversible engine. So, this is the first postulate of Carnot. The second postulate says that within this temperature limits, if we have got number of reversible cycles, number of devices which are operating on reversible cycles, then all the heat engines or all the cycles will have the same efficiency. So, it will not depend on the working fluid we are using, it will not depend on the size of the cycle we are using, it will not depend on how many processes are there in the cycle, but if the cycles are reversible, all of them will have the same efficiency. Then you see that in this thing 2 points are very important, or 2 attributes are very important, that is T1 that the source temperature and T2 is the sink temperature. If T1 and T2 are given, then we will get best performance of a cycle working between these two temperature when it is operating reversibly, and when it is operating reversibly its efficiency is constant, because all the reversible cycle will have the same efficiency. Its efficiency is constant means its efficiency now it will depend only on T1 and T2, because these two things only we have specified. So, let us make a broad step. We have defined the efficiency of heat engine. So, let us say efficiency of heat engine. Let me draw it once again. Q1 heat is taken, W work is produced and Q2 heat is rejected. Q1 heat is taken from reservoir at T1, Q2 heat is rejected to the reservoir at T2, W work is produced. So, efficiency from the first law we have got as W by Q1. So, that is 1 minus Q2 by Q1. So, now we know that efficiency is dependent only on the temperatures T1 and T2 if this engine is a reversible engine, and this is of course beyond the course, because it is not a course of thermodynamics. It can be shown with some sort of a logic that efficiency of a reversible heat engine can be expressed as 1 minus T2 by T1, where T2 is the sink temperature and T1 is the source temperature, but these are the absolute temperature or temperature according to thermodynamic scale. So, this is a very important, very important consequence of second law of thermodynamics, that for reversible heat engine we are getting 1 minus T2 by T1, that is the efficiency of the reversible engine. Basically, for reversible heat transfer, what we get, if the engine is operating reversibly, then we get the heat transfer processes are also taking place reversibly. Then for reversible heat transfer process, what we get is this: Q1 by T1 is equal to Q2 by T2, sorry, Q2 by T2. So, if we get this, and this can be seen how it has been obtained in any book of thermodynamics, then from that it logically follows that the efficiency of a reversible engine will become 1 minus T2 by T1. So, now you see that higher the T1, the more will be the efficiency of the reversible engine. So, when we were having this introductory lectures of waste heat recovery, I have told that waste heat recovery, for waste heat recovery we have to look into two aspects. One is quantity of waste heat we are getting, and another is the quality of waste heat we are getting. So, here we get some sort of a quality concept of quality of energy, which is also given by second law, that quality of energy, quality of thermal energy is associated with the temperature from which the thermal energy is extracted. So, you see quality of waste heat, that is also related to the temperature from which or at which the waste heat is available. So, now probably we can relate what we have studied or what we have discussed in some previous lecture, that quality of waste heat, that will be that will be dependent on the temperature at which the waste heat is available. So, then for converting waste heat very usefully, profitably, not only the amount of waste heat which is available, that is important, it is also important at what temperature that waste heat is available. The higher the temperature, suppose the waste heat we are utilizing in a heat engine to produce some sort of work, more work can be produced if the waste heat is available at a higher temperature. Same amount of waste heat is available at a higher temperature, we can extract more work. The waste heat same amount again is available at a lower temperature, we will not be able to extract the same amount of work out of it, the equal amount of work out of it. When it is available at low temperature, we will have lesser amount of work out of it. So, this is very important, and we are getting also the concept of quality of energy from this. Let us now see with this principle what could be the COP. So, again this is at temperature T1, and we are having a cyclic device which is operating in the reverse direction. Work is supplied from outside. It is taking Q2 amount of heat from a reservoir which is at T2, where T1 is greater than T2, and supplying Q1 amount of heat to a reservoir which is at a higher temperature at T1. So, this can be seen either as a refrigerator or as a heat pump. So, COP reversible refrigerator, that will be Q2 by W, that is equal to Q2 by Q1 minus Q2, and as it is reversible, we can write it will be T2 by T1 minus T2. COP reversible heat pump, that will be Q1 by W, and that is equal to Q1 by Q1 minus Q2, and in terms of absolute temperature we can write T1 minus T1 divided by T1 minus T2, T1 upon T1 minus T2, and as T1 is higher compared to T2, we will have COP of heat pump more than 1. Same thing what I have told earlier. So, you see now the ideal performance of these two devices, heat engine and heat pump, that is available or that is known to us. So, obviously, I have told in previous lecture, the best strategy of waste heat recovery is to produce no waste heat or produce the least amount of waste heat. Best strategy of energy conversion will be produced to convert it in the most efficient way. So, now from second law we know that if we have adopted the most efficient way of energy conversion, what could be the figure of merit of these two important devices, one is heat engine and another is heat pump. So, as far as this discussion is concerned, this is very useful for both energy conversion and waste heat recovery. And then we have also got the idea regarding the quality of energy. So, quality of energy, particularly when it is thermal energy, so that is directly dependent on the temperature at which it is available. So, that holds good for waste heat also. So, quality of energy, again let me tell you one thing, we have got energy in transit, there are two forms, one is work and another is heat. For work there is no division, but heat or thermal energy, there is something associated with it, that is temperature. So, work is the highest quality of work is having the highest quality of energy, then or it is the highest grade of energy. Then heat or thermal energy is a lower grade of energy. Again in heat or thermal energy, there could be division, there could be again different quality of the thermal energy, and that quality depends on the temperature at which that thermal energy is available. So, now I think with the second law of thermodynamics, this picture is clear, and with this information at our hand, we can proceed for planning, for designing, for selecting different waste heat recovery techniques or principles, and again for equipment selection also this helps us. With this, I like to end today's lecture. In the next lecture, we will come to another important concept, that is entropy, and from there we will go to exergy. Again these concepts may be known to many of you, but for the sake of completeness we will do this, and then with that we will come to an end to our discussion on thermodynamics, which is relevant for waste heat recovery.